Well, hello there, Year 11. We're starting on a slightly new area today. We're still in Chapter 1, but we're moving away from sequences and series and into an area known as proof. We're going to be looking at three different ways of proving that something is something or equals to something else. And so this is going to take all of this week, at least, probably all of this week, and then we'll move into another area next week. So we're still in Chapter 1, but just a slight change of scene. Methods of proof. Now this is pure mathematics at its very best. We're just proving stuff. You know, here's one statement. Prove that it's equal to this statement, or prove that this can be true, or this can never be true. So really fun area. You'll feel like real mathematicians, I think, doing this work. And also an interesting thing about mathematical proofs is that once a proof has been validated, a mathematical proof that is, then it can't be refuted. It's set down in stone. It cannot be disproved, if you like. So mathematical proofs are very powerful, and they're great fun. So let's get to work. Okay, so we're going to look at in this section, as I said in the intro, mathematical proof. Okay, now there's we're going to look at three methods of proof, as I also mentioned, and so we'll just outline those three areas now. The one we're going to look at today is known as direct proof, and direct proof is really just proving that one side equals another, left-hand side equals right-hand side, using proofs. Using properties, using theorems, axioms, algebra, essentially, to prove that one side equals another, and working in a logical fashion. Then we have a really interesting method of proof by contradiction. So we end up contradicting ourselves. We end up saying something ridiculous that means that what we started with must not be true. So we contradict ourselves. We start off with assuming that what we're trying to prove can't be the case, which is really interesting. And then we're going to look at a method of proof by mathematical induction, which is a method by which you prove that some statement works for a single value, usually the lowest value, the smallest value that you can substitute in, or that you're trying to prove for. And then you prove that if it's true for a particular value in your statement, then it has to be true for the next value. And so then it generates this domino effect. So the mathematical induction proof. Okay, so here we have the three types of proof that we're going to look at. Today it's direct. Later in the week, like tomorrow, it'll be by contradiction. And then we'll probably spend a couple of days on mathematical induction. We've got 4 sessions this week. There's 4 sections to our OneNote, and perhaps I'll just go through that for a second. So we're in here at the lesson creation section. All right, so this is week 3. This is where we are, and what I'm looking at doing is covering 3 areas, E, F, and G of the exercises, all due Monday, the 4th of May. So complete. There will be a quiz on Friday. There may be some exit tickets thrown in. I'll let you know if I add those, and I'll put those in here because the mastery checkpoints. Oh no, well there'll be I'll let you know. This is an evolving document. These Zoom class catch-ups. These are for these are optional essentially. There's no point coming to a Zoom if you haven't done the work, and so what each link tells you is what it's to do with. So the first link is to do with direct proof, which is this lesson, and that's on Monday at 9 a.m. So that's the week. You can post your questions there, and if you want to book a one-on-one tute, you've got a couple of questions, and you think Zoom will help out, then go through that link there. So that's and always I will have my notes to all of the lessons will be in here in screencasts. Okay, so that's the layout of the week. Now, we're just going to go through a few examples just to show you how these things are laid out, and then you can get on with the exercise. So the first example is show that 1 plus 3 plus 5 plus equals n squared. So what we're going to do here is we're going to start out with left-hand side. So we're going to go left-hand side equals, and we're going to proceed logically using what we know and arrive at the right-hand side. Now the left-hand side is, this is relatively new knowledge for us, but it's an arithmetic series. So we can say it's an AP where our first term is 1, our difference is 2, and our number of terms is n. Okay, so we can therefore say that 1 plus 3 plus 5 plus 2n minus 3 plus 2n minus 1 is equal to, right, we've got n over 2 terms. Our first term is 1, so it's 2 times 1 plus n minus 1 times d, which is 2. Alright, now this is equal to, once you expand, you get n plus n by n minus 1, which is n plus n squared minus n, which is equal to n squared, and then we triumphantly announce that that's equal to the right-hand side as required. Now that's really what we're doing with direct proof, is that we just proceed logically. We use what we know, use what properties we have in our tool bag, and off we go. Right, I'll write out the next example. All right, in this example we're going to go through some fairly typical types of direct proofs, and that is some different properties to do with odds and evens, etc. So let's go through them. Show that the sum of an odd and an even positive number is always odd. So what we should outline here is that an even number can be represented as 2 times some integer, right? So n is an integer, and an odd number we can represent as 2 times some integer plus or minus 1. It doesn't really matter. P is an integer. Okay, so that's how we're going to get around these types of questions, by representing even and odd numbers in this way. So, right, with that in mind, let's do some proofs. So A will be prove that the sum of an odd and an even positive number is always odd. All right, so we can say therefore that, let's say the sum of an odd number, so that's 2p plus 1, and we're going to add an even number, so we'll call that 2q. All right, so this is the left-hand side, so I should say left-hand side is equal to, how should we do this? Prove that odd plus even equals odd. All right, so I'll say left-hand side equals, all right, so my odd number is equal to 2p plus 1. My even number is 2q. Okay, just a note, I could have used any letter here. 2q is just follows p. Okay, so I want to prove it's odd, so I want to show that it's twice something plus 1. So I can group these to 2p plus q plus 1, right, which is odd. Okay, I could say since p plus q is an integer, left-hand side is odd. So therefore, it's equal to the right-hand side. That's sort of what we're doing here. Now the thing we should do is whenever we introduce variables, we should define what they are. So when I introduced here that the left-hand side was 2p plus 1 plus 2q, which was my odd plus my even, I should just therefore note that p and q are integers. Right? This guy here, remember, is the symbol for an integer, and then group it. These are fairly trivial once you get the hang of them. The sum of two even numbers is always even, so I want to prove that even plus an even is equal to an even. Okay, so I'll say the left-hand side is equal to an even number, which is 2m. I'll add another even number, which is 2n. I can't use the same letter. All right, I'll just note here that mn are integers, stating the obvious, but we have to. Right, now this can be grouped to 2m plus n. Right, and since m plus n are integers, is an integer, it's equal to a even number, which is what we've got on the right-hand side. And C, the sum of two odd numbers, so prove odd plus odd is equal to an even. Perhaps pause the video here and have a go at this yourself. So now rewriting this as odd number left-hand side is equal to, I'll go with 2m plus 1. An odd number to n plus 1, where m and n are integers. This is going to equal 2m plus 2n plus 2, and that's m plus n plus 1, which is an even number since m plus n plus 1 is an integer. And that's my right-hand side. An even number is what I was trying to prove. It was equal to my right-hand side is even. Okay, so they're fairly typical. You'll see some of those in the exercise. Okay, fairly straightforward example here. Show that we're really just looking at. There's nothing too challenging here algebraically. It's really just becoming accustomed and familiar with proving something, showing something, and you'll have done a little bit of this already. So any proofs that you have been asked to do up to this point have been direct proofs, because they don't require any special techniques. Really, you're just proving logically one side equals another. So in this case, we've just got this fairly ugly bit of algebra here, and we need to simplify it. So we'll just say here that the left-hand side on expansion will equal x squared, and perhaps again it's better for you to pause the video and work ahead and then come back to this. X squared plus, I'm squaring this, so I've got twice the product of ax over 2, which is just going to be ax, and then the square of a over 2. All right, so that's a squared over 4. And then I subtract the square of a over 2, which is a squared over 4. So I end up with x squared plus ax, which is equal to the right-hand side. And our job is done. Okay, in this example, we're going to proceed in much the same fashion. We'll say that the left-hand side, let's expand it out. We need to do something with it. Although there's n plus 4 there, can we just drag an n plus 4 out as a common factor? Perhaps we'll just expand out. So n squared plus 8n plus 16 minus 3n minus 4, which equals n squared plus 5n plus 12. Now just have a little look over the right-hand side there. And what we see here is we see an n squared plus 5n plus 4. So we can see with the plus 8 it's going to equal this. So what I might do now, just to help me arrive at this is to rewrite this as n squared plus 5n plus 4 plus 8. So that's a logical step, which allows me then to factorize to n plus 1, n plus 4, my first three terms, plus 8. And now I can announce that I have the right-hand side as required. To write on the same line, you don't want to be working with both sides at the same time on the same line. So what you can do is you can say left-hand side equals, and you can proceed as we did where you got to plus 12, and then you can say right-hand side, go to another line of working, and write the right-hand side equals n squared plus 5n plus 4 plus 8, which equals n squared plus 5n plus 12, and therefore left-hand side equals right-hand side. So that is valid, that is good. I can give that a tick and that a tick. What is not okay, and really important to highlight here, is that it's not okay to say to work on both sides simultaneously on the same line. So what I mean by that is n squared plus 8n plus 16 minus 3n minus 4 equals n squared plus 4n plus 1. Sorry, plus 1. What am I doing here? N squared plus 4n plus 1n, n plus 4 plus 8. I'm demonstrating a way that's not okay. So then we'd say, therefore, n squared plus 5n plus 12 equals n squared plus 5n plus 12, and therefore left-hand side equals right-hand side. I want to show there that that is not okay, and the difference between these two methods are that we worked here separately. Left-hand side and right-hand side were not worked out on the same line, whereas here they're worked out on the same line as if they are equal, and proceeding through as if they are equal is an incorrect method. So worth distinguishing between those different types of proof, because when we're concentrating on methods of proof, we have to make sure we're being absolutely spot on. My preferred method is to just fashion the left-hand side to look like the right-hand side. So the first method here would be my preference. If you would like to work with both sides, just make sure you are doing so on separate lines and in separate sections, not in this method here, where you are on the same line, and that is a big no-no. Put a big cross through that. Okay, next example. Okay, here's a really interesting example. Prove that if the sum of the digits of a 4-digit number is divisible by 3, then the 4-digit number is also divisible by 3. So a little bit like the odds and evens, we need a way of representing a number, okay, so that we can break the digits down. So we can do it in a few ways, but I'm going to show you one way. I'm going to say that n is equal to the 4-digit number, A, B, C, D. Okay, so where A is equal to n is equal to A times 1000, because that's the place value of the A, plus B times 100, plus C times 10, plus D. Okay, so we're breaking the 4-digit number down into its place value, and what we know though, importantly, is that the sum of the digits is divisible by 3. So we can say that that A plus B plus C plus D is equal to some multiple of 3. So let's say 3k, where k is an integer. Okay, so this is a slightly odd question, as in it's not odd. You're familiar with the divisibility test, etc. But what you might not have been asked to do before is to make such a proof. So in order to do so, we need to look at a number and break it down into its digital components, because we are concerned with the sum of those digits. So we need to represent A, B, C, and D individually as numbers, but we also need to represent this 4-digit number as a number. So we need to look at it in two ways: as A times 1,000 plus B times 100 plus C times 10 plus D. That's my N, that's the value of my number. Where A plus B plus C plus D, the component values of those digits, are a multiple of 3. So this is my information. Okay, so here we go from here, and you may not think of doing this, but hopefully you will when you see an example in the exercises. I can say from here, from this equation here, that D, I'm just going to let D, I'm going to make D the subject. So I'm going to take D and make it equal to 3K minus A minus B minus C. Now, you'll see why in a moment. I'm going to get back to N, so therefore N is 1000A plus 100B plus 10C plus not D, but 3K minus A minus B, minus C. Okay, now let's do a little simplifying now. I've got put my A terms together, so I get A by 1000 minus 1. I get B by 100 minus 1. I get C by 10 minus 1. And I get 3K. So if you expand that out, 1000A minus A, that ticks off my A terms, plus 100B minus B ticks off my B terms. 10C minus C ticks off my C terms, and then I've got my 3K there. So it's starting to take a little bit of shape. A by 999. I might just write this. Plus 99B plus 9C plus 3K. Remember, this is my N. What I'm representing here is N in a way differently to how I started there, using the fact that the sum of the digits is a multiple of 3, rewriting D in terms of A, B, C, and K, and that allowing me to rewrite my N in this way. So let's, we're pretty close now. So that's equal to, okay, 999A plus 99B. We can say that 3 is a factor of all of these terms, so we'll factorize it out, and we get 333A plus 33B plus 3C plus K. Now that is right, so what we've got in brackets here, this here, that is all a, this is a multiple. Sorry, not a multiple of 3. Sorry, this is an integer. Because A, B, C, and K are all integers. We had that right at the start. A, B, C, and D obviously are integers. K was brought in as an integer. So this expression here is an integer, and that's all I need to show to say that N is a multiple of 3, because I've got 3 times an integer. Okay, so therefore, I can say now, therefore, N is divisible by 3. Okay, so that's probably going to do us. You can now head into a bit of practice yourself with exercise 1E, and I think we can do all those questions. Okay, I'll catch up soon.